This content is for informational purposes only and does not replace professional medical advice. Always consult a qualified healthcare provider for personal health concerns. Have you ever wondered what actually happens inside your body the moment a vaccine enters your system? Most of us think of a vaccine as a simple shield, a straightforward delivery of immunity, but the reality is far more intricate and fascinating. Tucked away inside those vials is a silent partner, a substance that acts as a catalyst, an invisible coach that trains your immune system to recognize threats with greater precision. We call these components adjuvants. Without them, many modern vaccines would struggle to spark the powerful, lasting response that keeps communities protected. It is a common misconception that the active ingredient does all the heavy lifting alone. In truth, these specialized compounds are the secret architects of long-term health, working behind the scenes to ensure your body doesn't just see the pathogen, but remembers it for years to come. Why are they necessary, and how exactly do they amplify our natural defenses without compromising safety? There is a profound sophistication to how these ingredients interact with our biology, turning a fleeting encounter into a permanent memory for our white blood cells. As we pull back the curtain on this medical marvel, we will examine the history, the chemistry, and the rigorous science that governs their use. Understanding the function of an adjuvant is key to grasping the full story of immunization, moving beyond the surface level to appreciate the precision engineering that defines contemporary medicine. By looking at the specific mechanisms these substances employ, we can better understand the balance between potency and safety that researchers strive to maintain. Let's shift our focus to the initial breakthroughs that changed the way we approach disease prevention entirely. Those early breakthroughs were driven by a simple, yet profound realization: sometimes, the body needs a gentle nudge to recognize a potential threat. This brings us to the core of our discussion today: the definition of an adjuvant. When scientists develop a vaccine, they typically use an antigen, which is a small piece of a virus or bacteria designed to teach your immune system how to identify a specific pathogen. However, in many cases, that antigen alone is a bit like a whisper in a crowded room. It might not be loud enough to grab your immune system's full attention. This is where the adjuvant steps in. When introduced alongside an antigen, they don't necessarily provide immunity themselves, but they significantly boost the body's internal reaction. Research suggests that these substances help create a more robust, long-lasting memory within your immune cells. By prolonging the presence of the antigen at the injection site or by signaling to your body that it's time to pay closer attention, adjuvants ensure that your immune system doesn't just glance at the threat, but instead archives the information for future protection. The antigen is the photo, but the adjuvant is the workshop that forces the immune system to engage, analyze, and store the details of the intruder. Studies indicate that this process is vital for vaccines that use inactivated or purified components, which might otherwise be cleared by the body too quickly to trigger a meaningful defense. By slowing down the delivery or by activating specific sensors in your innate immune response, adjuvants help bridge the gap between a fleeting encounter and a durable shield. The goal is to stimulate a strong enough response to build lasting immunity without triggering an overreaction. This balance is why researchers spend years fine-tuning the exact composition of these boosters. Because our immune systems are incredibly complex and varied, finding the right partner for each antigen is a cornerstone of modern immunology. By understanding the specific categories of these helpers, we can see how different designs work in harmony with our biology to provide the protection we rely on. Building on that idea of a specialized toolkit, we have to ask ourselves, why do some vaccines struggle to get the job done on their own? When a new pathogen enters, this network needs to be alerted. For some vaccines, the antigen, the piece of the virus or bacteria we are using to teach the body, is like a quiet whisper in a crowded room. Without a little extra help, the body might not mount a strong enough response, leaving the door open for an infection later on. Research suggests that for an immune response to be truly effective, it needs to cross a specific intensity level. If the antigen alone is too weak, the body might produce only a fleeting, shallow defense. They act as a signal flare, ensuring that the immune cells, our sentinels, don't just notice the threat, but actively engage with it. By creating this heightened state of alertness, these helpers encourage the body to recruit more soldiers, produce more antibodies, and crucially, commit the experience to memory. We aren't just looking for a temporary spike in protection. When an adjuvant is included in the formulation, it often creates a depot effect, keeping the antigen present in the system for a longer duration. This extended exposure allows the body to refine its defenses, resulting in a more precise and persistent immunity. By lingering at the site of injection, the adjuvant ensures that our immune cells have enough time to study the enemy, practice their response, and solidify their strategy. This leads to higher levels of circulating antibodies that remain ready for action months or even years down the road. By optimizing the immune response, we can achieve better protection with fewer visits to the clinic. Now that we understand the necessity of this boost, we can start to examine the specific physical and chemical structures that make these helpers so effective at their jobs. As we look closer at these immune-boosting components, it is only natural to wonder how they interact with our physical well-being. This is where the conversation around safety, comfort, and the vetting process becomes vital. Most people who receive a vaccine containing an adjuvant will experience nothing more than mild, localized feedback at the injection site. These aren't signs of danger, rather, they are physical markers confirming that the adjuvant is doing exactly what it was engineered to do. By creating a temporary, controlled environment of localized inflammation, the adjuvant alerts your immune cells to gather at the site and begin their assessment. Beyond these common, short-lived reactions, some individuals report systemic sensations like a low-grade fever or mild muscle aches. Research suggests these are consistent with the immune system shifting into a higher gear. Because these reactions are predictable and generally resolve within 48 to 72 hours, medical professionals view them as a standard part of the process. It is important to acknowledge that the development of these substances is not a hasty endeavor. Scientists spend years, sometimes decades, mapping out how these compounds behave in the human body. They track everything from how the body metabolizes the adjuvant to how it is eventually cleared from our systems. The vetting process is designed to ensure that the adjuvant stays exactly where it is needed, at the injection site, long enough to do its job, before being safely processed and discarded by your natural metabolic pathways. This balance is the cornerstone of modern vaccine safety. When we look at the data, the vast majority of safety concerns are addressed by this meticulous oversight, which prioritizes long-term health outcomes while minimizing discomfort. To truly appreciate how they function, we must investigate the specific molecular architectures that allow these compounds to act as such effective catalysts for our immune memory. To understand these molecular architects, we have to recognize that not all helpers are built the same way. The most seasoned veteran in this field is the aluminum salt. They work primarily by creating a localized depot effect, essentially acting as a slow-release mechanism that keeps the antigen present at the injection site long enough for immune cells to take notice. Research suggests that these salts also help organize the antigen into a structure that is more easily recognized by our defensive sentinels, effectively acting as a chemical signal flare. As science has progressed, we have moved toward more sophisticated delivery systems, such as oil and water emulsions. By mimicking the structure of certain pathogens, these emulsions can stimulate a broader and more nuanced response. Studies indicate that this technology is particularly effective at waking up the immune system in scenarios where a standard antigen might otherwise be overlooked or ignored. It is a more targeted approach, designed to maximize the efficiency of the response while minimizing the amount of antigen needed in the vial. These newer technologies are essentially biological keys designed to fit into the specific locks on our immune cells. Rather than just creating a physical barrier or a depot, these compounds communicate directly with the cellular machinery. They send precise biochemical instructions that tell the immune system exactly how to prepare for a specific threat. The beauty of this evolution lies in the diversity of the toolkit. We are no longer limited to one-size-fits-all solutions. Instead, medical professionals have the ability to select the right partner for each specific antigen, ensuring that the body receives the most appropriate guidance to build lasting memory. Yet, even with these advanced tools, the final success of the process depends on the intricate dialogue between these compounds and the complex environment of our own biology, a relationship that we are only just beginning to fully map out. As we look toward the horizon of immunology, The next frontier in vaccine development is shifting from broad-spectrum support to precision-engineered molecular partners. Researchers are currently pioneering synthetic adjuvants designed to act like a precise compass for the immune system. These cutting-edge compounds are being crafted to interact with specific cellular receptors, effectively acting as a volume knob for our internal response. By refining these interactions, scientists are moving closer to a future where we can achieve robust, long-lasting immunity with significantly smaller doses of antigen. This evolution not only promises to stretch global vaccine supplies further but also holds the potential to unlock cross-protection, the ability for a single vaccine to guard against multiple variants of a virus or even entire families of pathogens. Imagine a vaccine that can adapt its signal to stay ahead of viral mutations, providing a more versatile shield than ever before. We are witnessing a transition from simple alarm bells to sophisticated coaching systems that teach the body exactly how to recognize and neutralize threats with unprecedented efficiency. To wrap up our journey, let's synthesize what we have learned today. Adjuvants are the unsung heroes of immunization, acting as essential facilitators that help the immune system identify and remember antigens. They shorten the time needed for protection to develop, strengthen the intensity of the antibody response, and reduce the amount of vaccine material required for each individual. By understanding these mechanisms, we can better appreciate the science behind the shots that protect our communities. In short, vaccines are not just an antigen alone. They are a partnership between a specific target and the carefully chosen boost that ensures our body takes notice and learns a lesson well. This content is for informational purposes only. Please consult a doctor for health concerns. Thank you for watching and for taking the time to understand the intricate biology that keeps us resilient.